Swayam Prabha. Digital India. Educated India.
So, welcome back again. So, today I present I continue the same, but I simulate the conservative form. So, because we are solving the conservation equation, and then it is better to solve the conservative form because we have taken before the primitive form. So, the conservative form looks like del rho by del t plus del by del x. So, this f of rho was a function of rho square by 2 is equal to 0. So, this is the conservative form. So, it is a derivative of the flux function. So, now this is again I take minus 1 to 2, same example like before. So, my domain is minus 1 to 2 and some initial condition. Same like earlier, rho of 0x is again 1 if minus 1 less equal to x less equal to 0, 1 minus x if 1 less equal to x less equal to 0 to 1, and 0 if it is between 1 and 2. Again here, so this is 1, this is 1, this is 2, this is our x direction, this is our rho 0 of x direction. So, this is 1 here up to here, 1 minus x and 0. So, this is our initial value. So, 1 here, 1 minus x here. So, I am using more or less same example such that you will be reprogramming, you will be writing your own code what I have produced. And now what we have now, this is our flux. And then here we our final time step t of final is equal to 1. So, after that, after 1, what we will have, we cannot have any solution. So, let n be the number of grid points. So, grid size is equal to 2 minus of minus 1 is 3 by n. Grid size delta x is equal to 3 by n. Now, the grids are xi is minus 1 plus I minus 1 of delta x. So, I run from 1 to n, and the discrete value rho of I is rho of xi, I again is equal to 1 to n. So, these are our discrete form. So, what does it mean? That I have my domain -1 to 2. So this is the x1. So here x2, x3. So this is equal to my x of n. So I have my discrete value here, somewhere something like that. So I have my initial discrete value, or these are like this. Yeah, so here it is 0. Now, so naive approximation of the flux. So it is rho square by 2. So del y del x of rho square by 2 is this. You can take it half out because it is constant. Take it outside the derivative. And now what you get, that rho of I plus 1 square minus rho of I minus 1 square divided by 2 delta x. Yeah, this is our derivative central difference scheme. So we hope maybe with this conservative form it works. Let us see. Now the time integration. So the time integration, rho of I n plus 1 minus rho of I n by delta t. It may be boring, but it will be repeating for you so that you can understand better. Plus, now this term is there. It's a half rho I plus 1 square at time level n square minus rho at time level n I minus 1 square divided by 2 delta x. This is equal to 0. And now here we have that. So this implies we get our scheme rho I of n plus 1 is equal to, here I put on right hand side, minus half delta t by 2 delta x. So 2 to 4 you can write, but now leave it. Then inside the brackets, rho n I plus 1 square minus rho of n I minus 1 square. So this is the scheme number 8. So the equation is 8.0. The scheme number is 8.1. So this is the naive approximation. Now what we can have, that once if it fails, then we'd have to do again the upwinding. So how upwinding looks, it is not much difficult. So let me write on the top my equation 8.0 here. So this is my master equation, del rho by del t plus del by del x, rho square by 2 is equal to 0 minus 1 to 1 2. So this is my master equation 8.0. So now I do, if it fails, the central difference or naive approximation fails. So now we do the upwinding. Same idea as before. If it is positive, we follow from the left. If it is negative, we follow from the right. If rho is positive, or the approximation of the flux, del by del x, rho square by 2 is equal to half. I take it out. rho of I minus rho of I minus 1. Yeah, is I minus 1, I plus 1. So if it is positive, so I take these 2 points. Yeah, if rho is negative, I should take rho negative, I should take this and this point, because the information going from here, information coming from here. So if rho is negative, del by del x, rho square by 2 is equal to half. So then I take rho I plus 1 minus rho of I. And now the upwinding scheme looks like, if rho positive, then toward final time integration, rho of n plus 1 minus rho of n by delta t plus half rho of I n square minus, so here it should be square, sorry, this is the square, rho of I minus 1 n square, this square bracket is equal to 0. If rho negative, rho of n plus 1, here it should be index I again, rho of I minus rho of I n by delta t is a plus half. So here divided by delta x again, because here I should have divided by delta x, so divided by delta x. Here rho of I plus 1 n square minus rho of I n square divided by delta x. Yeah. So if we put all together, what we will get? If rho positive, we get rho n plus 1 of I is rho of I n minus, put it on the right hand side, delta t by 2 delta x, rho of I n square minus rho of I minus 1 n square, the minus here. If, let me write in the language, computer language form, else if rho of I n minus 1 is negative, we get rho of I n plus 1 is equal to rho of I n minus delta t by 2 delta x, rho of I plus 1 n square minus rho of I n square, this one. So this is for the positive row, this is 8.2. For the negative row, this is 8.3. Yeah. So this is the conservative form of original Burger equation. Now in the earlier lecture, what we have said that there is also the viscous form. So what viscous form is? So a viscous form has, so I think it should be clear. So with the original conservative form without viscosity, right hand side 0, we have this scheme. Now what will happen if I have the viscosity here. So if there is a viscosity, so we add instead of 0, so what we add? Epsilon del rho del second derivative of rho, yeah, if there is a viscosity. And then what we have, we already remember that del 2 rho by del x square is, so it is rho I plus 1 minus 2 rho of I plus rho of I minus 1 divided by delta x square. Now, so in that case, what we add? With the naive scheme, we add here on the right hand side plus we add that term. So delta t plus epsilon times delta t divided by delta x square. So on the right hand side, exactly that viscous term, second order derivative, rho I plus 1 n minus 2 rho of I n plus rho of I minus 1 n. So this is with the viscous form, in the conservative form of viscous-Burger equation. And here again, what we will have, the same term here, plus delta t epsilon times delta t by delta x square, rho of I plus 1 n minus 2 rho I of n plus rho of I minus 1 n. So this is the viscous form. And this 8.3 also exactly the same, not much different, plus delta t by, so epsilon times delta t by delta x square, same term here, I put it rho of I plus 1 n minus 2 rho of I n plus rho I minus 1 n. So this is the upwinding scheme for viscous-Burger equation in conservative form. This is central difference scheme for viscous into the conservative form. If like in the primitive form, what we had, that if the epsilon was not large enough, we got the oscillation of this scheme, and if epsilon is very same small epsilon, we did not get any oscillation here. It was then finally with the small of epsilon, we are getting close to the exact Burger equation. Now, what was the difference is that in the primitive variable, we have again simplified this one. We took the derivative, and then we got, instead of that, this is equal to rho del rho by del x. Yeah. So this is the difference between the earlier primitive form and now this is the conservative form. Now let us see the numerical example, whether we are able to reproduce same result as the earlier case. Let us see some MATLAB code again. So let us say our MATLAB code. It is nothing different. So I am taking again the epsilon is 0.001. And so here normally our velocity is here. It's the maximum of rho. So it is maximum value of rho is 1 here in our initial condition here. So what I have described. Now again, so this is my domain -1 to 2. Here I generate, so I define my n and I define my delta x. So once I have that, I generate my grid point in the regular basis, and I do the initialization here, this loop. If so, I run from value the grid point 1 to n. If x is negative or -1 to 0, then I have my density is equal to, this is equal to 1. if it is between 0 and 1, so my density is falling linearly, is 1 minus x. So if it is between 1 and 2, it is 0. So which I have plotted initially on the board. And now I just define my new value, which is rho n plus 1. And so same as my old value, which is rho n, I have to assign from new to old, because if I do the time iteration. And now here I start my time integration. So I run when t is less equal to t final. So my t, I start with t is equal to 0. So which is the initial condition given from this condition here. So I run only for the interior point, because I am excluding at the moment boundary point in order to avoid the I minus 1. If I is equal to 1, I have rho 0. So I have not defined x of 0. Therefore, I am taking 2 to n. If it is I plus 1, I have n plus 1. The n plus 1 value also I don't have. Therefore, in order to avoid all the complexity, I am taking interior point 2 to n minus 1. So, and I just keep that boundary value is 0, because the wave doesn't reach to the boundary. Now I start with the central difference without viscosity, this formula here. So my new rho is equal to, so here I think I made a small mistake here. It should be a rho of ni rho of I n minus, because writing it, so it should be like here, minus delta t times 0.5 is half, and times I divide by 2 delta x here, this part here, times this rho old of I minus 1 rho of, so this is for the positive case, yeah. So this is a rho of I plus 1, the old, minus rho of I minus 1 old, and square, so nothing else. And then after that I update my time from t to t plus delta t, and then I plot at every time step the solution, and then I redefine my old value, new value is as old value. So I just overwrite my old value as a new value, and then I do the iteration until, so here my time integration ends. So finally I plot the exact solution of Burger equation. Since in the earlier lecture we have derived the exact solution, then we want to match the solution, numerical solution, with the exact solution. So let us see what will happen. So here my epsilon is 0.001. So again we got the oscillation here, so it is very bad. So the solution blows up because of this central difference. Let us play with the earlier form. So if I take larger, 10 times larger viscosity, what will happen? We still get with the conservative form. With the primitive form we did not get that, we got little bit smearing solution. So here somehow the conservative form gives us more accurate solution than the primitive form. In the primitive form with the same viscosity, which I have shown you in the earlier lecture, with the 0.01, we were getting here in the shock little oscillation, but here with this conservative form we got very bad unstable solution. Now let us do what will happen with the if I apply the operating scheme. Now everything is same, yeah. So I take 100 point. Now what I have here, the flux, if rho is positive, here exactly same. If rho is positive, so I define my flux is a backward difference. If rho is negative, I define my flux as a forward difference here. and then my rho nu is rho old plus the flux function. So delta t by delta x times that flux function. So other thing is same, it doesn't change. Now let us see how a solution looks like. So I have plotted with the line, not with the point, so I can also plot with the point. So here we see that in the earlier case, in this scheme, what we are getting, that already in the beginning we have the oscillation, but here we avoid the oscillation. Here we get very smooth solution. So it means that our grid point is not fine enough so that we get little bit smearing solution. Let us see plot in the final time step how our exact solution at t is equal to 1. What is the difference between the exact solution and numerical solution, what we get. So here this is our exact solution, is the blue one, and this is our numerical solution. Now let us decrease our epsilon. So we take epsilon even 10 times smaller than that. What will happen? Let us check. I have not tested, so let us test together. So even until now, no sign of oscillation. Oh, here I have not. Yeah, it doesn't matter. So sorry, because this is the time I don't have any. So I don't have any epsilon. So I was confused with the earlier example. Now we come to our viscous form. Yeah. Now what will happen? So now we have seen that upwinding scheme gives us a nice solution. Now the viscous form that I take, like with the central difference viscous form, we get oscillation like earlier. Now what we will have that, so I have this scheme, positive and negative flux at the density. So let us see with the viscous form, yeah, the conservative form of Berger equation with viscosity. So my viscosity is here 0.001. Is the epsilon is 0.01. So it is 400 points. So we can run with the 100 points later. So now it's still going on because of large point. It is taking a little bit longer time. Now let us come to the end of the solution as t is equal to 1. So we are still running at t is equal to 0.75. So it is so we are almost to the end of the time integration. So reaching t is equal to 1. Then we stop simulation. So now here we see that it is getting very stable solution, which was not given by this one. Now let us decrease our viscosity. It was very smearing because our viscosity was too large. Now I make viscosity smaller, and also instead of 400 points, I take only the 100 points. So our simulation runs faster. So even for the 10 times smaller viscosity with the upwinding approach, we are getting the stable solution. So with this lecture, I somehow finished the finite difference scheme, because now next I speak with the Meshfree scheme, which is generalized finite difference scheme, and therefore I was giving you a little bit impression of finite difference scheme so that you will understand the coming lecture, which is basically based on the finite difference scheme. So now let us come to the end of the simulation. Now even with very small epsilon with 100 points, we are getting better solution. So now we stop with this finite difference idea today. So thank you very much for your attention.